So let's look at the equilibria. So ion exchange equilibria can be written in the ionic form. Let's say A plus ions, it has a charge N, so let's say A N plus ions from the liquid are getting exchanged with B ions from the resin. So R is the resin, and because the charge is N, we will require N atoms of N ions of B, and so they will be in equilibrium with A getting loaded onto the resin and the B will come into the solution. So like we define equilibrium by a constant KAB, and you can write this in terms of the loading of A in the resin, concentration of B in the solution raised to power N, divided by loading of B into the resin divided by concentration of A raised to power N in the solution phase. So this KAB is called as molar selectivity coefficient for A displacing B. For dilute solutions, KAB is typically constant for a given pair and a given resin. You can think about this KAB in terms of it as a ratio of Ka divided by Kb, just like we do it for liquid-liquid extraction. The individual values of K and Kb are called as relative molar selectivity for A and for B. So what we will do is we will see some typical values of KAB and then we will solve a problem. So typically, let's say we are looking at cations on a strong cation exchange resin. The relative molar selectivity for various cations is listed here. So for example, if we say that potassium has a relative molar selectivity of 2.9, whereas H plus is 1.3, that means if the resin is in H plus form, it will be favorable for it to be exchanged into with the potassium ions. So if you say if we say A is potassium, B is hydrogen ions H plus, then KAB would be 2.9 divided by 1.3. It will be more than 1. So it will be favorable for K plus to get exchanged with go into the resin and H plus to come out from the resin. And you can see the relative molar selectivities of different ions, and you can use this as a guide to see which one will get favorably exchanged into what form of resin. Similarly for anions, this is with strong base anion exchange resin. So if you say OH minus ions in the resin form, it has a of type 1. Let's say it is has a molar selectivity of 0.05 to 0.07, and you can replace it with, let's say for example, chloride or bromide or nitrate. They will have higher molar selectivity. So if we say A is nitrate and B is OH minus ions, then the KAB would be 4 divided by 0.05. So it will be very favorable for the nitrate ions to go in the resin and OH minus ions to come out of the resin. So let's take a small problem. Let's say there is an ion exchange resin. It has a maximum ion exchange capacity of 4.9 milliequivalent per gram on a dry basis, which translates into 2.3 milliequivalents per ml of the resin. This is used to remove, let's say, copper ions from 9.75 millimolar, which is same as, because it's a divalent ion, it is same as 19.5 milliequivalents per liter of the copper sulfate solution. The following data give the equilibrium for copper plus ions between the resin and solution. What I would like you to do is calculate the molar selectivity coefficient KAB for the copper ions to go inside the resin and H plus ions to come out from the resin. Take care of units, express all concentrations in terms of milliequivalents per ml or gram equivalent per liter. They are same. So do this problem, pause the video, do this problem for yourselves and then see the solution. Okay, so here is the solution. So let's just take one data point. Let's take this last data point for example. So if we write now all the concentrations in the solution phase, in the solution phase H plus would be there at equilibrium, that would be 19.5. That is the concentration of original concentration of, or initial concentration of copper in the solution. And let's say if we say that out of this 19.5, let's say 10.3 has remained in the solution. That means 19.5 minus 10.3 has gone inside the resin. So if you say correspondingly 19.5 minus 10.3, 9.2 milliequivalent per liter of H plus ions would have come into the solution. Copper plus that has remained in the solution at equilibrium is 10.3. Now we do a balance in the resin phase. So resin initially had 4.9 milliequivalents per gram or 2.3 milliequivalents per ml. So 4.9 minus 4.65, that is what is copper that has gone into the resin. So this difference must be the H plus ions that have come out. And if you want to write in terms of per ml, so that we need to multiply this by this multiplying factor. Same way, copper ions in the resin phase would be 4.65, that is what has gone inside per gram. On dry basis, you need to multiply this by 2.3 divided by 4.9 to make it into milliequivalent per ml. Now Kab we can calculate as the copper in the resin phase 2.183, H plus ion in the solution 0.0092, square of that, H plus ion in the resin phase 0.117 square, and copper ions in the solution, that is 0.010. So Kab would be 1.31. If you take from the previous table for copper replacing H plus, copper is say 3.8, H plus is 1.3. So copper replacing H plus would be 3.8 divided by 1.3. You will get 2.9. Obviously this is for one data point. You don't need to do it for all data points. What you actually need to do is plot a curve of Cu2 plus and H plus square in the liquid phase, this on y-axis versus this parameter on the x-axis, and then slope of that line would give you the Kab, because each individual point would have experimental error. So we are not going to find Kab from individual points. We are trying to find a Kab over this whole range. Therefore, we will do regression for this whole data. Now let's take another problem, continuing with the same problem. Now suppose we have a 10 liter of 20 milliequivalent per liter solution of copper 2 plus, and we would contact with 50 grams of dry resin with a capacity of 4.9 milliequivalent per gram. In terms of the wet, it is 2.3 milliequivalent per ml. And let's say Kab is to find out the percentage exchange of copper ions at equilibrium. Again, use these formulae and do the problem yourself. Once you have done, you can go forward and check your answer. Okay, so if you have done the problem now, let's say suppose X is the milliequivalent of per ml of copper that is remaining in the solution. What was initially present? It was 0.02 milliequivalent per ml, right? So what is the copper ions on the resin form? It is 0.02 minus X, that is what has gone in the resin phase. 10,000 is just because we are using 10 liters, so that is 10,000 ml divided by 50 milliequivalent per gram of the resin. So that is divided by 50, that is grams of resin. That will give you milliequivalent per gram of resin that is remained in the resin phase at the equilibrium. So this is per gram of resin. If you want to represent in terms of ml of resin, just have to multiply this multiplication factor. Same way, concentration of H plus ion in solution is what has come out from the resin, 0.02 minus X. Concentration of H plus ions in the resin would be 4.9, that was the capacity, minus what has come out into the solution divided by the weight of the weight of the resin that is taken, multiplied by this correction factor. So now we can write an equation for Kab in terms of these unknown X. This is one, this is another, third and fourth. So all these four terms will have will be dependent on X, and Kab is told to you Kab is 2. So then you can solve for X. So if you solve for X, what you will get is X equal to 0.00113. That means percentage of copper ions exchange would be 0.02 minus 0.00113. That is small. This is the error is 0.0113. Just solve for yourself. So which would mean that 94.4% of copper has got exchange. Sorry, there's no correction. X is the amount that is remaining in the solution, that is 0.00113. So this should be 0.00113. There is the correction here. Okay, so this would be 94.4%. Okay, so here is the corrected value, 0.02 minus 0.00113 into 100 divided by 0.02, that is the 94.4% exchange of copper ions. So you can see, because Kab is 2, how favorable it is for ions to copper ions to get exchanged, and particularly because we have used 10 liter of solution and 50 grams of resin. Now we can think about how to optimize this to get a certain degree of recovery and so on and so forth. Now ion exchange and adsorption adsorbents are rarely used in the free form unless you are having very specific application. Very often they will be used in a ion exchange or adsorption columns. So we'll see a little bit about this as well. So if you think about a column which is packed with adsorbent or ion exchange resin, the solution flows from bottom to top or top to bottom in this particular case. Now you see that the solution is flowing around these particles. So there is first of all a boundary layer resistance for the transport. So there is a first resistance is the external mass transfer resistance, and inside the particle there are pores. So the second resistance is the transfer of the solute into the pore and then adsorption or ion exchange onto this active site. So there are different resistances, and if it is in the free form, obviously the boundary layer resistance is less because we can agitate the resin. But when it's in a column, you are limited by what velocity with which column can be operated. So the boundary layer resistance or the external mass transfer resistance can be a significant portion of the total resistance. So we need to account for all these resistances, and we typically represent all this in terms of some one kinetic constant, the rate of ion exchange or the rate of adsorption, and we will see where that appears in the column operation. So if you think about this column, this is an idealized operation. When feed comes from one end, let's say from one end to the other, this is the adsorbent material that is fed inside. So as this feed comes, the initial part of the resin gets saturated, and now then it can no longer adsorb. So this then the subsequent part of the resin or the adsorbent gets loaded, and then the subsequent, and so on and so forth. So what you see is a front of adsorption. So this part of the bed is completely saturated with the solute. No longer adsorption is happening here. The feed is simply coming here, and this is where the adsorption starts happening. Adsorption starts to happen. Adsorption or ion exchange starts to happen, and the remaining part of the bed, it has still not seen any ions or any solute from here. So this is still the ion exchange resin or the adsorbent is in the free form. It is still not adsorbed anything. So you can idealize the situation. You can think about this as an adsorption front. If the kinetics are very fast, then this adsorption front will be just a straight line. We will have a clear demarcation between the bed that is at equilibrium with this incoming feed solution and the bed that is free. So in this part, if you plot CF, that is concentration in the of the solute. CF is, let's say, is the feed solution. So the feed solution concentration does not change till you come to this adsorption front, and then because the adsorption is so fast, it becomes essentially zero, and then beyond the length, beyond this part of the bed, the concentration is zero. So this part, no adsorption is happening, no ion exchange is happening because it is already at equilibrium. So then we call this as the length of the equilibrium section or weight of the equilibrium section of the resin. This part we call is length of unutilized bed or weight of the resin unutilized unutilized in the bed. Now this will have this idealized operation. This will happen if the adsorption process is extremely fast. In reality, obviously that is not true. So what happens is this adsorption front is not a sharp interface, but is a diffuse interface. So if you think if you plot concentration on this axis versus length, concentration is zero, let's say here, and it progressively increases to the feed concentration at, let's say, this length of the bed. So you get this would be an adsorption zone. We can hypothetically think that this would be the adsorption front, but actually there is a adsorption zone. Sometimes some books call it as mass transfer zone. This is the zone where mass transfer is occurring from the solution phase into the resin phase. And as we put more and more solution, this adsorption front is progressively moving down. Then this part of the adsorption front comes, so if you think in terms of, if you see here or here or here, the concentration at the exit. So if you say CT versus C0, CT is the concentration coming out divided by C0, that's the feed concentration. So CT by C0 is 0 here. The adsorption zone has not yet reached the end of the bed. So there is still an unused portion, and therefore the concentration becomes 0. But now this mass transfer zone, if it just reaches the exit of the bed, then this concentration just starts to increase. So this is called as a breakthrough time. It's as if the solute has started breaking through the column. And if we continue with respect to time, we will see that the concentration at the exit keeps on increasing, and finally when all the bed is exhausted, it reaches the equal to the inlet concentration. So the bed is completely exhausted. We call this as the exhaustion time. This is a breakthrough time. And if you think in terms of an idealized bed operation, then this TS would be an idealized breakthrough time. Okay. So mathematically, if you want to represent, how would you we could represent this as, if you think about this area under the curve, right? So area under the curve between 0 to TE. It is this area, therefore 1 minus CT by C0. It is the area of this curve, this shaded portion. Right, let me just drop pen. Yeah, this shaded portion, area of this shaded portion. Right, this whole thing. That is how much material has gone into the bed. Now, in terms of an idealized representation, this in terms of an idealized representation, the amount adsorbed could be thought of as a rectangle with this as the idealized breakthrough time. So the idealized breakthrough time would be, this would be the amount, and if you could represent in terms of the, if you could represent in terms of the area of a rectangle, it would have time equal to TS. So that's the meaning of this TS. That's an idealized breakthrough time. So the length of the unutilized bed would be, so length of the bed divided by T. So this TS is now an idealized breakthrough time. Now length of the unutilized bed we can write in terms of length of the bed divided by TS. That would be the velocity with which the adsorption front or mass transfer front is going down into the column, or going into the column with respect to with the velocity with which it is traveling in the column. So this velocity multiplied by this difference, T minus TS, that would be the, or you can look at it either way, TS minus TB would be the length of the unutilized part of the bed. So the length of the equilibrium section of the bed would be the total bed length minus the length of the unutilized part of the bed. And length of the equilibrium section also we could write from the amount that is getting adsorbed. So QF is the flow rate, C0 is the initial or the inlet concentration. So this would be the rate at which the solute is coming in, multiplied by time. This is the total amount of solute that has come in, divided by the volume of the bed, and QE would be now the equilibrium in equilibrium with this C0, the equilibrium loading in equilibrium with C0. So this you can get from adsorption isotherm, and actually some of the resin in the bed would not be accessible as that in a free form. So this QE also can actually be a fitted number. What is the equilibrium value of the solute inside the resin or inside the adsorbent in equilibrium with this C0? This QE can be actually back calculated from the length of the equilibrium section. It may or may not be equal to the value that we have measured from isotherm. Usually it is slightly lower than what we measure from the isotherm. Now this is the breakthrough curve plotted in terms of time, but we could also think in terms of the breakthrough curve in terms of number of bed volumes. So this would be QF multiplied by T divided by volume of the bed. Now this is easier to think in terms of how many bed volumes of the solution has passed. So for example, if bed is, let's say, 1 liter, and breakthrough time occurs in terms of, let's say we have processed 20 bed volumes. So it becomes easier number to visualize how much volume can be processed through a given amount of bed, and it can become easier for scale up purposes. Now if we go forward, let's take a small problem. So imagine that water vapor is getting adsorbed from nitrogen gas using Fourier molecular sieves in the lab scale adsorption column as given below. So bed length is 0.27 meters, like 1 foot bed. Temperature is 28 degrees centigrade, pressure is 6 bar absolute. Nitrogen molar flow rate is 145 kilomole per hour per meter square. Inlet water content is 1440 ppm by moles. Bulk density of the bed is 710 kgs of the adsorbent per meter cube. Okay. What I would like you to calculate is length of the equilibrium section, length of the unutilized bed. Also calculate what is the effective equilibrium concentration of water vapor on the zeolite, 4A, in terms of grams per kg corresponding to inlet concentration of 1440 ppm. This is the data of breakthrough. So 0 to 9 hours, no water vapor is in the exit, everything is getting adsorbed. 9 hours 1 ppm, 9.4 hours 9 ppm, and so on and so forth. You can see that after 13 hours the bed is completely exhausted. Whatever is the inlet concentration, everything is coming out of the bed. So try this problem yourselves, and once you have completed, you can see the solution. So pause the video, try this problem yourself. So here is the solution. So first of all, from breakthrough time, let's say breakthrough time TB is 9 hours, at which the break happens, concentration in the water in the exit starts increasing. Bed exhaustion time is 13 hours. Okay. Now to calculate TS, what we need to do is plot this graph of 1 by CF by CF, or you can say concentration at the exit CT divided by C0 in terms of the concentration that we have been, in terms of the notation that we have been using. This is CT by C0 if you like, or concentration of water vapor at the exit divided by the feed concentration. Now you can take this data. Now from 0 to TB, this integral we can split into two integrals, 0 to TB and TB to TE. So 0 to TB and TB to TE. So that 0 to TB integral is, everything is getting adsorbed. So 1 minus CF by C0. So your CF is 0. So this is 1 minus 0. So this is just TB. Now the second integral TB by TB to TE, 1 minus CF by CF, you can actually integrate using Excel or using trapezoidal rule and things like that. You will find, do this yourself, don't trust the value, just do it yourself. You will find that TS becomes 10.93 hours. So the length of the unutilized bed comes from this formula. So length of the bed 0.27 meters divided by 10.93. That's a idealized front velocity multiplied by 10.93 minus 9, TS minus TB. So the length of the unutilized bed is 0.048 meters. Okay. Length of the equilibrium section would be total bed length minus 0.048, that will be 0.222. So the length of the equilibrium section indicates that the bed length that is saturated with respect to inlet feed concentration. Inlet feed concentration is 1440 ppm. Since 1440 is very small, we can think in terms of 1440 divided by 10 raised to 6, 1 million, as 0.00114 kilomoles of water vapor per kilomole of nitrogen. So kilomoles of water vapor removed from the incoming nitrogen till a time TB, that is this time, okay, would be TB would be 145. 145 is the molar flow rate, right? So 145 multiplied by 9 hours multiplied by 0.00114. Now this is using TB. We have not used TS, right? We are only using TB, just to be on the safe side. So this will tell you 1.88 kilomoles of water vapor is removed per meter square of the bed. Now mass of the adsorbent in the bed up to the length of the equilibrium section. So because we are using TB, we are using length of the equilibrium section. Okay. So that will be 0.222 into 710. So 0.222 is the length and into 710. 710 is the bulk density. So this means kilograms of the resin is there or adsorbent is there per meter square of the bed. So equilibrium loading would be 1.88, that would be kilomoles into 18, that will give you kilograms, multiplied by 1000, that will give you grams, divided by this 157.62, that will give you 214.7 grams per kg. So that is how much is the equilibrium loading of the water vapor onto the bed or into the adsorbent 4A zeolite adsorbent at the concentration of 1440 ppm in the vapor phase, because this part of the bed, this part of the bed is the equilibrium section. Equilibrium has been reached, equilibrium is reached, and no more adsorption is happening in this part of the bed. So that is the equilibrium. That equilibrium is 214.7 is at a concentration of 1440 ppm. So we can check with the actual isotherm and see whether this is higher or lower. We can use it in a different way as well. If we know the total volume of the bed, we know the total volume of the bed, in this particular case 0.27 is the length, multiplied by, if I take 1 meter square, we'll know how much is the bed volume, multiplied by 710, that will tell you how much is the mass of the adsorbent in the bed per unit area. And now if we know the equilibrium value, actual equilibrium value, we can calculate how much percentage of the resin or how much percentage of the adsorbent is actually used. So this equation can be used in different ways and it can also be used for scale-up purposes. Now there are some models which have tried to model this breakthrough curve. Let's just very quickly see that. So there are some models. One of the oldest models is Thomas model. It says this CT by C0. CT is the concentration at the exit, divided by C0 is the feed. Sorry for using different notations in different parts. I will try to correct it. So this would be 1 divided by 1 plus exponent of kth. Kth is a kinetic constant, tells you how fast the adsorption is occurring, takes into account all the mass transfer resistances and diffusion resistances, actual rate of the adsorption or rate of the ion exchange. QE x by q, x is the total weight of the adsorbent in the bed, minus kth C0t. So C0, kth again is the rate constant, C0 is the feed concentration, and T. So you can predict the outlet concentration as a function of time if you know these parameters. Alternatively, if we know this outlet concentration as a function of time, we can fit these parameters to the data and use those fitted constants for scaling up or for trying to look at what happens if I have a different bed and so on and so forth. Yoon and Nelson model 1984. Again, this the model is CT divided by C0 minus CT, but is equal to exponent of KYN. Now that's a kinetic constant into time minus KYN divided by tau. Tau is the time required for 50% of the feed concentration in breakthrough. That means in terms of the dimensionless values, if you say 0.5 here, the value here would be tau e. The value here would be the tau in the Yoon and Nelson model. Now this model we can rearrange and write in terms of very similar to Thomas model. We see that there is a good similarity between this model and this model. So they are not really very different models. They are the one and their expressions are identical. Clark model, this assumes that Prundtlich isotherm is valid and the Prundtlich adsorption constant is n, and this model says that CT divided by C0 is 1 divided by 1 plus a exponent of minus RT whole thing raised to 1 upon n minus 1. So A and R now are the model constants and you can use this to predict, or if the breakthrough curve is known in terms of CT as a function of time, we can use it to back calculate the model constants A and R. 2005, another model was proposed called as bed depth service time model. So this model form is given like this. Let's not go into derivations. So Ka is the model constant. It's like the kinetic constant. C0 is the inlet concentration. N0 is the equilibrium adsorption capacity. Z is the depth or length of the bed, and V is the velocity. So again, this expression, if you rearrange, we can rearrange it in terms of CT divided by C0 would be 1 divided by 1 plus e raised to this parameter. Now you can compare that this model and these two models, they give the same expression. So they are not really very different models. The expression is the same. It's just the physical meaning is slightly different, but each one of them contains a kinetic parameter. Each one of them contains a time form. Okay, so here is a small problem. The breakthrough curve from the previous problem. This was the breakthrough curve for the previous problem, water concentration in the exit. Fit the breakthrough data of this BDST model, bed depth service time model, and use this fitted parameters to estimate constants for other models. Okay, so do this problem for yourself, and once you're done, you can go forward. Pause the video now. So if you want to fit this model, bed depth service time model, what we will do is plot a data of time on the y-axis versus ln C0 by CT. C0 is the feed concentration, CT is concentration at any time t minus 1 ln of this term, and then you will get slope and intercept. Okay, so here is the data that is plotted. Time on the y-axis, ln C0 by CT minus 1 on the x-axis, and this is the data. And you can see that the fit is good, R square is 0.961, slope is minus 0.326, intercept is 11.01. Recall, intercept is A, so A is 11.01, slope is minus B, so B is 0.326, and R square is 0.96, so it's a good fit. So if you want to think in terms of how other model parameters would look like, compare this with the Yoon and Nelson model. So if you say A by B, that is your KYN tau. So compare this expression and this expression. So A by B is KYN tau, and 1 over B is KYN. Okay, yeah. So 1 over B is KYN, so KYN would be reciprocal of this. So 1 by 0.326 is 0.06, and tau would be 11.01. So now you can think of all these models: Thomas model, the Yoon and Nelson model, and bed depth service time model. Those are very similar forms. You can get one from the other. Now, if we have these parameters, now it is possible for us to predict for some other case. So what I'm trying to do is just to show you what is the effect of the parameter KYN. Remember, this KYN is like a kinetic parameter. It tells you how fast the adsorption is occurring. So what we'll do is we will take different values. So we'll take tau as 11.01 or 10 for this particular case. It doesn't really matter what value we take. What we are going to do is plot this CT by C0 versus T by tau. Okay, so CT by C0 of 0.5, this T by tau will be 1. See that? Now if we increase this KYN, that means the rate of adsorption is becoming faster and faster. It's as if we are eliminated the mass transfer resistance, or mass transfer resistance is smaller and smaller. Pore diffusion resistances are smaller and smaller. Adsorption is happening faster and faster. That means now the breakthrough curve is going to become behave more and more like idealized. That means the increasing this kinetic parameter, this breakthrough curve is going to become sharper and sharper. So if KYN was infinity, this breakthrough curve would have been just a straight line, the idealized breakthrough model. Look at this. Idealized breakthrough model. Right? So that's the meaning of this kinetic constant. The more and more mass transfer resistances are eliminated, breakthrough is going to become sharper and sharper. Operate the bed at higher and higher velocity, eliminate the external mass transfer resistance, reduce the particle size, but the penalty is pressure drop, and the breakthrough would become sharper and sharper. The advantage of breakthrough becoming sharper and sharper is the length of the unutilized part of the bed becomes smaller and smaller. You see, the meaning was a rectangle. If this is sharper and sharper, this difference between TS, TB and TE, they vanish, or they become smaller and smaller. So the length of unutilized portion of the bed becomes smaller and smaller. Effectively, we are utilizing more of the adsorbent from the bed. That's the advantage of writing these models and try to try to represent in terms of the kinetic coefficients and so on. Now these kinetic parameters you can use it for scale up. So for example, if you have to scale up to, let's say, from the pilot plant data or for the lab data, you have to design for the whole plant. What you could do is maintain the same velocity in the bed. So that means based on the flow rate, you will just increase the cross-section area proportionately to keep the velocity same. So if the velocity is same, adsorbent is the same on a lab scale and a plant scale, this kinetic parameter would be identical. And then you can use this kinetic parameter to calculate the breakthrough time, or if you know that you want a breakthrough after, let's say, 24 hours, you want the whole column to operate for 24 hours, then you can calculate what would be the length of the bed in the plant scale. So this is how we would use these models.